Hello, this is Questionable Coding with Vladimir, and today we're going to cover a data structure called linked list. It may seem like a trivial data structure, but in fact there are some hard implementation details. So we'll cover the implementation itself. We'll cover a general description of the list, most common problems that you can find out there on the interviews that are related to a linked list, and also we'll cover most common methods and algorithmic complexity of implementing those methods. So let's start with the description. We have a linear data structure which consists of nodes that are linked to each other. Also, we have a head that points to the first node, and this is the head of our linked list. Every node consists of two parts. It's data. It can be simple data like integer, and it can be more complex data like an object, and also a pointer to the next node. So our movement in the data structure is from left to right. Comparing with an array, which also consists of nodes, but we can access every node separately. So we can access like node with index 5 or index 1. In linked list, we don't have this ability, so we'll have to go from left to right until we face the node we want. And a lot of people are asking if does it make sense to use a linked list. Usually in a real world situation I don't see it, but linked list has its good parts. For example, it's very easy to insert an element there, and in an array this can be tricky because if you insert something in the beginning of the array, you have to recalculate indexes, and also you'll have to double the size of the array, as it's quite a common implementation of the array in languages. So yeah, linked lists will provide some help if you want to insert something, but usually you will face that structure during interviews, not like in the real world, at least in high-level programming languages. So let's check what are the most common operations for the linked lists or the methods. So in different implementations there can be different methods, and it highly depends on what you want. So if you need to get the length of a linked list, you can track the lengths. If you want something different, track minimal element, you can also track it. So be aware that you can alter the implementation just to fulfill your specific goal. But I checked the different implementations, and I think this set of methods is pretty common for linked list. First one is get element by index or get by index, and we just return like an element with index 2, let's say. And it looks like an array, but implementation is a bit harder. And add at index, we want to pass some value and create a node for that and insert that before the index. So if we'll pass index 0, we'll create a head. And delete at index, I think it's also pretty straightforward. At tail, I already also created a set of additional methods that can be used, or in some implementation they won't be there. For example, add at tail gives us it like push to the linked list, so we don't care what is the index, and we just add a new node there. And it's pretty nice when you don't know the lengths, so you don't know what index to provide. Otherwise, we can use the first method called add at index. Add at head is also very similar, so we can replace it by add at index 0, but we can have a shortcut for that, depending on whether we're gonna use it often or not. Traverse, we can go through the list and just output the list. It can also be useful if we need to output it. If not, then probably we don't need it. So it depends on what you want. Let's go through an implementation of a method called add at index. Let's say we have head, 3 elements, and head is pointing to the first element, and we want to add an element to the head. And we'll pass add at index 0, and we'll pass a value. So what we're gonna do is we're gonna create a new node, and right now our linked list doesn't know about it. And then we're gonna point this node to the current head, to the first element of the linked list, and then in the linked list we'll move the head pointer. So now we just added it with very little effort. In terms of computation, it may be tricky from code perspective. Another method we should cover is delete at index. So imagine we have a linked list with 4 elements, head pointing at the first one, of course, and then we're gonna delete the second element, I mean the index 2, because it's like the third element. We have zero-based indexes, as you remember. So we'll just, in fact, we'll first find the previous element, the red one, and we'll make it point to the successor of our element that we wanted to remove. So basically now it points not to our element but to the next one. And yeah, that basically removes the element. What about the complexity? So we have several methods like general actions, insertion, deletion, search. But we need to understand that usually it's specified that for insertion it's just a big O of 1. We need to understand if we want to first find this node in the list, we'll have to go through it, so traverse it until we'll find this element. And it may require n operations, so it will be big O of n. But if we already have an element, we can have, for example, if we want to add a head, then we'll do it in big O of 1 complexity. So it differs. Usually it's specified that we can do it like instantly in a constant time. Deletion, the same thing. If we would just have a node to delete, then we can do it, but yeah, that's not that obvious. For example, we need a previous node to point to the next one, so yeah, usually it's specified as a big O of 1, but we can argue with this, I think. Sometimes it can require the full search in the array, so it will be big O of n. And the search itself, it's not aligned, but never mind. The search itself is big O of n, so if you want to search a node, then you'll have to go through, in the worst case, to go through the entire structure. But yeah, keep in mind that if insertion will include the search, then you have another complexity. So it's quite tricky for me, at least. And now we're going to go through an implementation. I already have, there is a task about designing a linked list on Leetcode, which will provide a lot of tests, and I think that's the most easy way to go right now. So I already finished this. We'll go through the code because you see it's a lot of code, and I'll give some comments about that. First of all, we'll have to create a data structure, like an additional object called node, which will hold the data and the pointer to the next node. And the list itself, the initialization will be also very straightforward. We'll have to have a head property and lengths. In my case, I want to track the lengths of the list. You can spare this property, but I found it very useful. So first of all, they want us to implement a method called get, and what we have here is we have an index, and we want, if index is invalid, we will return -1. So at first we need to see if index is more than this length -1. It's basically the last index, because indexes are zero-based and length is not zero-based. It just shows, so we will have to subtract -1. And if index is bigger, then we'll return -1. Otherwise, we'll have to create a counter and pick the first node this head, and then while counter is less than index, we'll go through to the next element by assigning node next to node, so node next to node, and we'll increase the counter. And when we're done with this, so counter reached our index, we'll just return the current node data. So this node will just change and change and change every time. It will just pick the next one by doing this operation. And yeah, in the end, we are sure that it's our node and we can return the data. Also, add at head. I think we can, yeah, let's go through it. So add at head is rather straightforward. We're given a value, and first we need to create a new node for that. We went during this process on slides. So, and we'll say that our current new node now points to the head. So node next equals this head. And now for the list, we'll just switch the head. So we have this head equals our new node. And we want to increase lengths because in my implementation, I want to track it right away. Sometimes you just don't need to do this step if you don't need the lengths. Edit tail is much more complex, but what we're gonna do, we're gonna remove this code and we'll reuse in both situations. We'll reuse a big method called add at index because it covers all cases, and we just need to provide a proper index and value for that. Should we go through this? I think so, yeah. So if index is more than length, and you see we don't subtract -1 because we, according to the task, we can specify the last, not existing, but last, if we'll look at the last index, we can specify the next index, so it won't have any element, but in that case we'll just add an element to the tail of our linked list, and yeah, it's described here. If index is greater than the length, the node will not, yeah, no, that's different. So if index equals to the length of linked list, the node will be appended to the end of linked list. Okay, and that one was a tricky thing because I made a mistake when I was implementing this. So yeah, it's a bit different. If our index is more than length, then we'll just return nothing. Yeah, in general method return void, so we'll just exit the method. And first we create a new node and we check if the index is 0, then we'll go with the head, with inserting to the head, and we already did it, so I think we'll keep it here. And then we'll create a counter. If it's other situations, we'll create a counter and we'll do the same thing. We'll just pick the first node, which will be the head, and we'll go through the entire array and yeah, just increasing the counter. And when we are there, when we are at the index, at the node that is previous to where we want to insert our new node, then we'll make all the magic and increase the length. And also we have delete at index. You see it's quite similar, so I think we won't stop on that. What we're gonna do is we're gonna replace this implementation with another one. First we'll launch it. It should be good, green. So I'll submit the task. There are around 50 tests, and yeah, they make sure that all edge cases are tested, and there are a lot of edge cases where you add something to the end or trying to remove something which is not there. So what we're going to do is we're going to replace the head with add at head with this, and how it's called, add at index. So this add at index, and we'll provide 0 because the head is index 0 and the value. And we'll do the same thing here. For this, we'll have to code this edit index. Oh no. Expression edit index, and we'll provide, we need the last index, and it will be this links. Yeah, I think just this links, because we want to create a new element at the end. And we'll pass the value. Let's execute it once again. Yeah, and it's also green. So that's how we'll implement the data structure. So to try your skills, I recommend this this task, which is called, you can find just a design a linked list task on Leetcode, and it has all the tests. You just need to use, just implement all the methods. And you see it's quite big comparing to other data structures that we saw before. That's why, yeah, I think it's done. And stay tuned, we'll cover more data structures in upcoming videos. I hope you'll like it.